And welcome back, College Algebra students. We are in Chapter 6, Section 2 today. We are taking a look at one-to-one functions and inverse functions. So we want to determine whether a function is one-to-one, so we'll first have to define that. Then we'll obtain the graph of the inverse function from the graph of a one-to-one function. We'll verify inverse functions, and we'll also find the inverse function of a function that's defined by an equation. Okay, so those are the things that we're going to try to do. Let's go ahead and get right into it. So the definition. What is a one-to-one function? So a function is said to be one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are indeed two different inputs of the function, then f is one-to-one if the y value, so if the f of x1 is not the same as f of x2. So previously we had defined a function as a relation between pairs of items, such that if we have a set of ordered pairs, every element of the domain was paired with exactly one element of the range. So our x's could repeat themselves and go to multiple different y values, but the x's could not be repeated themselves. Now what we're saying is the y values also now cannot be repeated. So a function is not one-to-one if two different inputs correspond to the same output. Let's take a look at a couple examples of this, and that way we'll get another view and perspective. So if we just take a look at this example here, determine whether a function is one-to-one. Says for the following function, the domain represents the ages of 5 males, and the range represents their HDL, or good cholesterol scores. As far as per milligrams per deciliter. So as we take a look at these, if we're just identifying, is this a function? So first off, is it a function? So for every x, does it only go to a single y value? So 38 only goes to one y value, 42 only goes to one y value, 46 only goes to one y value, 55 only goes to one y value, 61 only goes to one y value. So what we would say then is that this does indeed represent a function. Every age only has one corresponding cholesterol value. Our question here, however, asks us to determine if the function is one-to-one. So if it's one-to-one, what we're doing is we're reversing the process, and we're saying if I go from the range back to the domain, am I also a function? So does 57 only go back to one value? Yes, it does. Does 54 only go back to one value? Yes, it does. Does 34 only go back to one value? Yes, it does. Oh, it's 38 here. That's the dilemma because 38 goes to two different values. So if we reverse the process, it is not a function. Therefore, then, that makes this not one-to-one. Okay. So what we're looking for then, if we're asking, is it a function, as we go from basically the x values to the y values, okay, does every x only have one y? And in this case, we would. The y's can get repeated as we did down here. If 55 and 61 both went to the same value, that's fine if we're talking about a function. If we're talking about one-to-one functions, then we also have to be a function in reverse. So a function goes this way, one-to-one function also then means we have to be able to go back the reverse. Okay, so letter B, if we take a look at these values here, do I have any repeated values? That would be one way to think about this one. So -2 only goes to 6, -1 only goes to 3, 0 only goes to 2, 1 only goes to 5, 2 only goes to 8. So this is indeed a function because for every x, it only goes to a unique y. Does this work the same in reverse? For every y value, does we only get one x value back? So if my y value is 8, I only get one x value. Y value of 5, only get one x value. 2, same way. 3 works the same way. 6 works the same way. So yes, this is then a one-to-one function. Not only is it a regular function, but it's also a one-to-one. Let's take this graph out here. Letter B. Let's do it in the mapping notation. So we had -2, -1, 0, 1, 2. Okay. So if we take that group and then we say, okay, what's the next group? So we have our x's and our y's. Then we had, let's just do it in the same order that was listed, 6, 3, 2, 5, 8. So negative 2 went to 6, negative 1 to 3, 0 to 2, 1 to 5, and 2 to 8. Visually, this is I think, in my opinion, a lot easier to see. I only have one arrow coming off of each of my x values, so that makes it a function. When I go ahead, let's clean this up a little bit. So all of this went together. Now all of these are the same. When I go in reverse, so going from x to y, it's a function. If I reverse it, is it also a function? So 6 only goes to 2, 3 only goes to negative 1, 2 only goes to 0, 5 only goes to 1, 8 only goes to 2. So then that is, again, another way to look at, is this a one-to-one function? And it is. Okay. So one-to-one functions mean that every x only has one corresponding y, and for every y, we only have one corresponding x. Now, the formal definition up here is that any two different inputs in the domain correspond to different outputs in the range. So we can think about our x's and our y's that way as well. Okay. So when we were doing functions, we had what was called the vertical line test, where if we had a graph and we drew a vertical line anywhere in the graph, if we only touched the graph at one point, then we were a function. Well, we want to see if a function is one-to-one, we flip it, so to speak, and we end up with the horizontal line test. So the horizontal line test is exactly what it sounds like. If every horizontal line intersects the graph of a function in at most one point, then f then would be one-to-one. So if we take a look at the function that's listed, okay, this would represent a function because anytime I draw a vertical line, it only touches the graph at one spot. So that it definitely is a function. We have y equals f of x is a function. If we take a look at horizontal lines, however, so we've got this horizontal line here, because it touches the function in more than one place, then it is not a one-to-one function. So we can be a function, but not be a one-to-one function. If we take a look at a couple of other items down here, let's take a look then, so move this out of the way. Let's take a look for each function listed. Use its graph to determine whether the function is one-to-one. So we're going to use the horizontal line test here. These are functions that we have seen before. Some of the, our text calls them the library of functions. I've previously called them parent functions. I've used that in other teaching settings as well. So what we have is our basic graphs. If we have x squared, well, we know our basic graph of x squared. That's the U shape, and it does this shape. Okay, and then on letter B, we're going to have x cubed, and x cubed then looks like this. So I kind of missed my 0 in there, so let me come back, see if I can make that a little bit better. There we go, slightly nicer. Now, both of these are functions. If we drew a vertical line anywhere in the graph of A or the graph of B, we only end up crossing the graph at one point anytime we draw a vertical line. So it would make each of these functions. What we're asking now is, are they one-to-one functions? So if I draw a horizontal line, and if I draw it so it intersects the graph, now on letter A, we can see that it intersects at 2 points. So say that this was y equals 1. That means we know from our parent function that those would be x values of 1 and negative 1. So that would mean then that f of 1 equals 1 and f of negative 1 would equal 1. So that can be a function, but that's not a one-to-one function, because I have a y value that corresponds to two different x values. If I take a look at the x cubed function, as I draw horizontal lines through here, doesn't matter where I draw the horizontal line, it only ever crosses at one spot. So for every y value that I take a look at, okay, so let me come back through here and take a look at some y values. So if I do this one here, for this y value, I can read across and come up with a particular x value. So for that at y1, I come up with an x1. If I take a look at another spot, if I take a look at this y value down here, call that y2, I can read across and come up with this particular x value. Okay, so what that means, for every y value, there's only a single x value. So yes, this function is one-to-one. So another way to write that, instead of writing out in words, Okay, we can use symbols. We can write the number 1 with a colon and another one. That's another way to write this. So for every one y value, there's only one corresponding x value. Now, another interesting piece as we take a look at these, if I take a look at these particular examples, okay, um, on this first one, what we have is we have an increasing function. Okay, so for every x that we have, it's bigger than its y value is bigger than every corresponding x that was to its left. Okay, so as we keep on reading through this function, we keep getting bigger and bigger and bigger. So this graph here is an increasing function. The second graph is a decreasing function because it's consistently getting smaller as we go to the right. And the other function over here on the third piece is neither increase nor decrease. It's actually both of those. But what I want to take a look at on this case is as we take a look at either the increasing function or the decreasing function, if we would draw horizontal lines through here for either of these two functions, they do end up being one-to-one. Which leads us to our theorem that's underneath that. A function that is increasing on an interval is going to be a one-to-one function, because part of how we define increasing is for every new x value, so if I'm going to the right, for every x value on the right of the x value that was on the left, the y value on the right was bigger than the one that was on the left. And just the converse of that, or the reverse of that rather, for the decreasing functions. So every increasing or decreasing function will always end up being one-to-one. Now, this other graph up in through here, if I just draw a horizontal line, I see that this one is not one-to-one. Now, part of our homework in this section will be, if we're given graphs, can we decide whether it's one-to-one? Okay, so these three graphs here would be examples of something that we might see in our homework. Additionally, in homework might be, if we're just given equations, can we come up with the answer, is or are these graphs one-to-one or are they not? Okay. And then we have a second part. Okay, so the next theorem or definition then. So our next definition has to do with an inverse function. So this answers in part, why are we concerned about functions being one-to-one? Because the definition of inverse functions starts off with, it says, suppose that y equals f of x is indeed a one-to-one function. So we start with that. So if we have a one-to-one function, the correspondence from the range of f to the domain of f is called the inverse function of f, and we write this with f inverse. It looks like it's to the power of -1, but we don't say it's to the power of -1. We read that as f inverse. So, in other words, if y equals f of x is a one-to-one function, then f has an inverse function. F has an inverse function, f inverse, and x equals the f inverse of y. So if I take a function with y, it maps it back to x. So really what we're saying here then is if f of x gives me a y value, then I can have some other function that gives me the function with y as the input that gives me back to an x value. So I'm allowed to then reverse these. So I can reverse these, and I can reverse them because we are one-to-one. So another way to think about this is if xy is on one function, then yx is on its inverse function. So these will go back and forth to each other. Another way frequently we say this is if AB is in one function generically, then BA has to be on its inverse. So we can just flip-flop those back and forth very consistently. And that's what we're coming up with here on part 2. Obtain the graph of the inverse function from the graph of a one-to-one function. So again, just reiterating the concept, if we have some generic point AB, so some xy, so we're just going to AB in this case, is on the function f of x, then we reverse those, and that's got to be on the inverse function. So a function and its inverse are going to end up being symmetrical about the line y equals x. Okay, let's take a look at this and see what we end up with on why that might be true. So if I have a graph here, so if I come out to Let's call this A here, and let's do B here. Okay, so there's my point AB. So if I go ahead and draw then the line y equals x, and then I go ahead and come back through here and I say, okay, well, there's my A and there's my B, then it looks like maybe A would be up here and maybe B would be over here. Then here's my point BA, okay? And what we should see then is that these are the same distance on either side of that line. Okay? That's the concept that we are shooting for overall, as far as the idea of being symmetrical about the line y equals x. So with that in mind, let's take a look at this particular graph. And what we're saying here is that the graph in this particular figure does show a one-to-one function, y equals f of x. We don't know what the function is, we just have the graph. And we're asked now to draw the graph of its inverse. So when we take a look at a function, so if I have, looks like negative 2, 1, actually negative 2, negative 1 is on f of x, that means if I reverse that, negative 1, negative 2 must be on the inverse function. Negative 1, 0 is on the function. That then means 0, negative 1 must be on the inverse function. 2, 1 is on the function. That means if I reverse that, 1, 2, 1, 2 must be on the inverse function. So these are on f of x, and these are on f inverse of x. Again, notation looks like f with power of negative 1, but we don't say negative 1, we call that inverse. So when I come back and draw these points in, let's see, so if I was at negative 2, 1, I should also have the inverse at negative 1, negative 2. So negative 1, negative 2 would be here. Okay, so there's negative 1, negative 2. Negative 1, 0 now becomes 0, negative 1. And 2, 1 becomes 1, 2. Now I can go ahead and connect those. And what we will see, if I go ahead and draw the diagonal line y equals x, we should see that we have some symmetry across that line. So symmetry just means I could go ahead and fold this graph along this diagonal, and then 2, 1 would fold over to 1, 2, 0, negative 1 would fold over to negative 1, 0, and negative 1, negative 2 would fold over on top of negative 2, negative 1. So again, to repeat the idea, if AB is on f of x, then BA must be on f inverse of x. That is our overall kind of overall writing concept here that we're getting at as far as our inverse function. So another illustration here, if we want to verify an inverse function, let's suppose that f is indeed a one-to-one function. Then f has an inverse function. We call that f inverse. F looks like the negative one. We call that f inverse. So our figure down here, figure 14, shows the relationship between the domain and the range of f and the domain and the range of f inverse. And so if we take a look at, if we're mapping from the pink over on here to the blue, so if I'm going from left to right, so if I have the f function here, and I'm taking x, and I'm applying some function to that. So f of x goes back over here to this value. So we could say that is some kind of y value, okay? And then, so we have our domain here of f, and we have our range of f. If we reverse this, and this is the idea here, what if I go in the other direction? So if I go the other direction, then I apply, so I take f inverse of y, and I get back this x value over here. So if this is the starting piece, then this becomes the domain of the inverse function, and then the original domain of the function now becomes the range of the inverse function. So we have this interesting piece here where the domain and the range end up flip-flopping. And it does kind of give us that idea. If AB is in my function, then BA is in my inverse function. So the A's were all the inputs, or my domains of the function. B's were all the outputs or ranges of my original function. And then when we do the inverse, we reverse it. So the inputs, my domain of my inverse function, were the range, or was the range of my original, and the range of my inverse function was the original domain of my f function. So we see this fascinating concept into play that we can go back and forth. Now, if we want to verify that these are indeed an inverse function, what we need to show then is if I go ahead and start, let me clean this back up here. If I start with a particular x value in f, I need to be able to show, okay, that if I apply a function and then apply the inverse, I get back to x. So I end at the same place I started from. So I need to be able to go this direction and then reverse it back to this direction. That's one piece of it. The other piece says, well, what if I started over here at the range? I need to be able to show that I can go back this direction and then back the other way and end up with this same value. So I've got to be able to show back and forth both of those. Well, what this then overall represents is our composite functions that we looked at in our previous section. To verify that one function is the inverse of the other, we need to show that the inverse, or excuse me, not the inverse function, but the composite functions of both of those, both directions then, give us just our original input. So f of g of x, let me write this out in a little bit more detail. So f of g of x, I started with x, I applied the function g to it, and then I applied f to whatever this was. I need to get back to where I started from. Likewise, if I start with g of f of x, so I have an inside function, then I apply whatever this output is, I apply it as an input to g, that also has to give me back my original input. So the goal on this is that the idea of the inverse is whatever our function is, the inverse will take us back to our original output. Excuse me, back to our original input. So if I input x, I need to be able to get back out x overall at the end, and vice versa. So let's take a look. Let's take a look at example number 4 here. We want to verify that the inverse of g of x, which is x cubed, that its inverse is the cube root of x. Now, it seems to make sense there. If I have a number and cube it, and I take the cube root, I'm going to get back to the same number I started with. Let's go ahead and verify that, though, algebraically. So to verify, we have to show that we have to show this g of g inverse of x gets back x, and I need to show that g inverse of g of x gets back x. I have to show both of these. So I'm showing both directions. Okay, so let's take a look at. So let me say this: show, and also show that. Okay, so those are the things that we want to do. So let's start off with g of g inverse of x. So from our composite functions, we know that this means then that I'm going to have g on the outside and I want g inverse on the inside. Well, what was g inverse? By definition, g inverse was cube root of x. Now I want to apply the g function to this input. So what does the g function say? Well, the g function was x cubed, so my input cubed. So I'm going to end up with then the cube root of x. That's my input. And then my g function says whatever the input is, cube it. So if I have the cube of the cube root, the root and the power cancel, and I'm left back with x. So I've shown it one way. Now I've got to show it back the other way. So let's see what we end up with. So I end up with g inverse. So g of x is on the inside. So g inverse on the outside. G of x was x cubed. Now I want to apply the inverse function. So the inverse function is the cube root of whatever it is my input. So I want the cube root of my input. My input is x cubed. So again, similar to what we had on the previous item, the root and the power cancel out, so I end up with x. So yes, I've shown both ways. So I can say then, since g of g inverse of x equals g inverse of g of x, and those both equal x, g and g inverse are inverses of each other. Okay? So we can verify that those are indeed inverses. Let's take a look at the next group here. So let's see, we want to show that f of f inverse of x equals x, and we want to show that f inverse of f of x equals x. And then let's see, down over here we have our f of x and our f inverse. So let's see what we end up with. So on this first piece, f of f inverse of x means we have f of, okay, and what is our inverse? So we're doing our substitution. So the inverse function here was a half of x minus 3. So now we want to apply f to that. And so our f function says take whatever the input is, multiply it by 2, and then add 3. So I'm going to take 2 multiplied by the inputs, and then add 3. Well, what is my input here? My input is this half of x minus 3. So half of x minus 3. So 2 times a half is just 1. 1 times x minus 3 is x minus 3. And then plus 3. So minus 3 plus 3 goes to 0, so we're just left with x. So that side does work out to be okay. Now let's show the other side. Okay, so let's see. So we got f inverse of f of x. So that's going to be f inverse of, and what is f of x? So f of x over here, f of x is 2x plus 3. So whatever my input is, I'm going to double it and then add 3. So that's going to be 2x plus 3. Now I want to apply the inverse. Okay, so what is my inverse function? My inverse function says take the input, subtract 3, and then take half of it. So that's what it means here. X is our input. So we're going to take our input minus 3 and then take half of it. So we're going to take our inputs minus 3, and then we're going to take half of that. So it was, again, this was, half of our input minus 3. Let me do it this way. So there's our input minus 3 and then half of that. And what we're going to put in here is 2x plus 3. So as we do the order of operations here, we end up with 2x plus 3 minus 3. And so plus 3 minus 3 goes to 0, so we're left with 2x. And a half of 2x is just x. So again, showed what we wanted to show. So that means then, so since, let me say it this way, since f of f inverse of x is the same as f inverse of f of x, which is x, then we can say f of x and f inverse of x are inverses. So it's kind of odd here that we're saying show the f and f inverses are actually inverse because we're calling it the inverse. So we're verifying this and we're saying, okay, is this truly an inverse or not? So that's what we're showing. We had to show overall. And if we're trying to show these things, we have to come back with these composite functions and get both of these pieces back into play. So what if we want to go ahead and find an inverse? Okay, so we've verified what inverses are. We've looked at the graph of an inverse, but we haven't found the inverse of just an equation as yet. So let's go ahead and do that. So let's take the inverse of 2x plus 3. And interesting enough, 2x plus 3 is what we just had up here in green. So what we're going to do is we're going to figure out, well, how do we find out that the inverse then is a half of x minus 3? So if we weren't told that, how could we figure it out? So the concept, okay, is that if AB is on the function, that BA is on the inverse of the function. Or if XY is on the function, then yx has to be on the inverse of the function. So somehow we want to be able to reverse those. So let me go ahead and list the steps to finding an inverse. So let's do it this way: steps to find the inverse. Okay. So the first step that we're going to do is we're going to replace the notation f of x with y. So if we have up here, we have f of x equals 2x plus 3. So if we have f of x equals 2x plus 3, we're going to change this f of x to y. Okay, that is our first step. Okay. Second step then, notice that every xy in the function is the same as yx in our inverse function. So what we're going to do then is we're going to swap x's and y's. So every place there's an x, replace it with a y. Every place there's a y, replace it with an x. So over here, I'm going to write x equals 2y plus 3. Now what I want to do is normally when we have equations, we typically go ahead and have them solve for y. So that's what we want to do here. So let's solve for y. So I can say let's subtract 3 from both sides. And then I'm going to take half of both sides here. So instead of dividing by 2, I'm going to show it as a half, because if I show it as a half, then we can see this is a half of x minus 3, and that's going to show previously what we said it was going to be, 1/2 of x minus 3. And then step number 4, we're going to go ahead and replace y with the inverse notation. Notice at the beginning, we swapped f of x with y. At the end, we swapped back y with the inverse notation. And I'm going to go ahead and write this as the inverse first. So the inverse then is 1/2 of x minus 3. So we started then with f of x is 2x plus 3. We ended with this inverse 1/2 of x minus 3. And we know that this is okay. We don't have to verify this because we already verified it back up here in example 4. That's what we did over here. We showed then up here that f of f inverse, oops, I guess I left off parentheses there. F of f inverse of x was x, and f inverse of f of x was also x. So we verified in that example that they were inverses. And on this example here, let me squeeze it down here, we showed how to get the inverses. So this 4-step process is what we can do to go ahead and find inverses. Now, some publishers, some authors, some mathematicians will revise these ever so slightly. And so if you're looking on YouTube or you talk to another person, they might have an ever so slightly different way to go ahead and find the inverses, but they still work. We end up with the values over here. Now, the rest of our directions originally said find the inverse and then also graph on the same set of coordinate axes. Okay, so let's go ahead and see if we can go ahead and get that here. So if I have 2x plus 3, okay, let's see, so I got 1, 2, 3. It's going to be the y-intercept, and then up 2 over 1. Let's do again, up 2 over 1 is going to be up this way. So I'm going to end up with a graph that looks like this. So this is y equals 2x plus 3. Now this one over here, if I multiply that through, that's going to be a half x minus 3/2. Okay. So let's take a look at that one. So it's a half x minus 3/2. If I come down over here, 3/2 is going to be down in this region. Okay, and then I'm going to end up with a slope of up 1 over 2. So up 1 over 2 put me over here. Up 1 over 2 is going to put me back over here again. And so my graph is going to look like this. If I would extend these back out, extend that further, okay, then I graph y equals x. Okay. What we should see, now my graph is a little off here, that the distance here and the distance there would map out and be the same as each other. Let me go ahead and pull up Desmos quickly. Okay. And let me just get a new graph here. So we had 2x plus 3, and then we had 1/2, oops, 1/2 of x minus 3, and then let me also graph just y equals x. So if we go ahead and graph those in here, where to get this? Oh, okay. Yeah, so if I go ahead and have these in here, then we see this is supposed to be the line of reflection. So let's go ahead and dot that line. Okay, now we can see a little bit more clearly that these do appear to be inverse and symmetrical to each other. So they all meet down here at a single point, -3, -3. So this point here is 0, -1.5, or 0, -3/2. So that means it's not as reciprocal, but it's inverse then. If I flip-flop, these should also be in the graph. So if 0, -1.5 is on the graph, then -1.5, 0 should also be here. That should be this spot, and that's true. It fits. On this, we've got 0, 3. That means if we flip-flop these 3, 0 should also be in the graph of the inverse, and it is. So we see that these do match up quite nicely. Obviously, when we put in the graphing technology, it works out so much nicer than when we do it by hand. My hand wasn't off a huge amount, but we see it was indeed off at least some. So if I would have had lines, if I would have tried to do this on graph paper, would have looked quite a bit better. Okay. So now that we know how to find the inverse of a function, let's go ahead and find the inverse of f of x equals a rational function, 2x plus 1 over x minus 1, as long as x is not allowed to be 1. So why is x not allowed to be 1? Because if x is allowed to be 1, our denominator goes to 0, and then our function is undefined. So this would not make any sense overall if we were doing that. One other thing, let's just go ahead and come back up in through here. Let's go ahead and graph that at the moment. So we've got, let's see, 2x plus 1, and that's going to be over x minus 1. Okay. So there's our graph. So what we want then is we want the inverse of this graph. So we're going to try to figure out how to go ahead and flip this. So if at -1/2 0 is on the graph, then 0, -1/2 should be on its inverse. We should end up with something that's down over here. Let's see if we can come up with something. Oh, before we go on, let me come back up here and point one more item out. This function here, as we have listed, okay, this function is 1-to-1. If I take a horizontal line, anywhere I draw the horizontal line, I'm only going to cross this function. Okay, and again, this is a rational function because it's got two pieces here. I'm going to cross this only ever at one place. And so since I can only cross it ever at one place, it should then have an inverse. So let's see if we can figure out the inverse. So our steps, so step number 1, I'm going to replace f of x with y. So y equals 2x plus 1 over x minus 1. Step 2, I'm going to flip-flop x's and y's. So every place there's a y, I'm going to write x. Every place there's an x, I'm going to replace it with y. Step 3 said I want to now solve this for y. So my dilemma is I've got y's, I got multiple y's, I've got both the numerators and denominators. So one way to get rid of a variable in a denominator is to multiply by that denominator. So let me multiply both sides here by y minus 1. That means I end up with xy minus x equals, on the right side here, those cancel, so I have 2y plus 1. Now I've got at least no fractions, but I still need to get my y terms on the same side. So it doesn't matter which side we move them to. So just for example, let me move my 2y's over here. So I have xy minus 2y. And at the same time, let me move this x to the other side by adding. So that would be 1 plus x. So I added x to both sides, and at the same time I subtracted 2y from both sides. Okay. So over on the left hand side here, I've got two y terms, or two terms with y. So let me factor that y out. So if I factor the y out, from this first piece I'm left with x, from this other piece I'm left with minus 2. Over here then, normal convention is to write our variables first. So I'm going to go ahead and write x plus 1. Since I want y by itself, now in order to get that by itself, I'm going to end up needing to divide by x minus 2. So those cancel. So y now is going to be x plus 1 over x minus 2. And so we've now solved for y. So step 4, we're going to replace this y back with our function notation. But now it's no longer the function. It's now the inverse function of x. And so the inverse function of x is x plus 1 over x minus 2. with the caveat that x is not allowed to be 2, because if x is 2, then we end up with our bottom becoming undefined. Okay, so we're saying x plus 1 over x plus 2. If I go back to Desmos, so let's see here. So what I'm suggesting is we end up with x plus 1 over x minus 2. And so these should be inverses of each other. So on this graph, let me go ahead and make these a little darker here. On the blue graph, or I guess that's purple, on the purple graph, I have negative 1, 0. That means 0, negative 1 should be on the black graph, and that is, okay? And if negative 1/2, 0 is on my black graph, 0, negative 1/2 should be on the purple graph, and that is. And likewise, we could come up here with other graphs, other points, and we could see that they reverse each other as well. So this is 4, 3. So that means 3, 4 ought to be on the other graph. And it is. Okay, so it does appear as though graphically that we have found the inverse. Okay, so we're saying this is the inverse of our function. So we were successful. Find the function here is 1, 1. Find this inverse. So we did. Now we need to do the check. So let's go ahead and check the results. So the check here, we need to show that f of f inverse is x. And we need to show that f inverse of f of x is also x. Okay, so that's going to take us just a smidgen of time here. So let's see. So f inverse of x, we're saying is x plus 1 over x minus 2. And over here we still have our f of x. So let's see what we can start here. So let's do f of f inverse of x. Let's see, so the inverse of x goes first. That's our substitution. So we got x plus 1 over x minus 2. Now we want the f now evaluated at this input. So our function is twice the input plus 1 over the input minus 1. So let me go ahead and write this out here. So it's going to be twice the input plus 1 over the input minus 1. And our input now is x plus 1 over x minus 2. Okay, so that is all the substitutions. Now what we need to do is we need to simplify. Okay, and so to simplify, we're going to do some things that similar to what we've done before. So let me multiply both numerator and denominator by x minus 2. So in this first group, okay, let's see, I'm going to have the 2, and the x minus 2 and the x minus 2 are going to cancel each other out, so twice of x plus 1, plus, and then 1 time of x minus 2, which is just x minus 2. In my denominator here, the x minus 2 and the x minus 2 cancel, so I'm left with x plus 1, and then minus this value. So minus x, and then minus 1 times minus 2 is a plus 2. So let's finish this out here. And so what we have is 2x plus 2. So I'm going to have distribute here, and then plus x minus 2. In my denominator, I've got x minus x, so those cancel, and 1 plus 2 is 3. My numerator, I've got 2x plus x is 3x. 2 minus 2 goes to 0. I'm left with over 3. The 3's cancel, so I'm left with x. So that's what I want. I wanted f of f inverse of x to equal x. So that's good. Now what we need to show then is f inverse of f of x also equals x. So let's see. So f inverse, so f inverse of f of x, and f of x, again, was 2x plus 1 over x minus 1. So 2x plus 1 over x minus 1. Now I want to apply the inverse function. So the inverse function is up over here. We have our input plus 1 divided by our input minus 2. It's going to have our input plus 1 over our input minus 2. And our input this time is 2x plus 1 over x minus 1. So 2x plus 1 over x minus 1. 2x plus 1 over x minus 1. Then we're going to do exact same steps. We're going to end up multiplying now. In this case, instead of x minus 2, we're going to multiply by x minus 1 over x minus 1. So this becomes a big distributive property. So in this first case, the x minus 1's cancel. So I'm left with 2x plus 1, plus 1 of these x minus 1's, that's just x minus 1. In my denominator, x minus 1's will cancel, so I have 2x plus 1 again. But I've got minus twice of that, so minus 2x, and then minus 2 of negative 1 is going to be plus 2. Okay. So let's see, 2x plus x is 3x. 1 minus 1 goes to 0, so I don't have to worry about that. 2x minus 2x goes to 0, and then 1 plus 2 is 3. Similar type format, we did end up with x. So that then shows that f inverse of f of x gives me back my original input. So since I just showed then these two things to be true, that is the check that these are indeed inverses from each other. Okay. So we've got it. That is all of the content for this particular section. Okay. And so what we're looking for is the idea of the inverse. Okay, so we start off with one-to-one functions. If a function is one-to-one, then we can find an inverse. We went through graphically taking a look at that. We also have our 4 steps to show how to find an inverse and then how to check the inverse. So in order to check the inverse, we have to go ahead and show both directions work. So if AB is in the function, okay, then BA is in the inverse of the function. So f of x and f inverse of x. So we got to be able to go back and forth between those. Okay. Now, as just a little extra piece here, I do have a couple additional questions, and these are from the homework. And so the questions like what we will see for sure. So let's take this this item here. So it says from the homework, the function f of x is 1 over x minus 2 is 1-to-1. So we're told it's 1-to-1. Let's find the inverse of f and check the answer. Then we'll find the domain and range of f and f inverse. And then we'll graph all of them on the same coordinate axes. Now, you notice over here, what I have is I do have all of the answers listed. So if I do 1 over x minus 2, what we're saying is our book is saying that the inverse should be 1 plus 2x over x. Let's see if we can go ahead and get that for ourselves. And at this point, this is the idea that I would encourage you as you're watching. Go ahead and pause the video and then do all 3 of these. Do A, do B, do C, and then go ahead and see if we agree in the answers. Now, you really don't have to necessarily restart the video because obviously the answer is already listed here, but I'll go through maybe a little bit more of an explanation on why those are correct. Okay, so on part A, find the inverse. So step number 1, replace f of x with y. So got 1 over x minus 2. Now I'm going to replace the x with y and y with x. And let's see if I want to solve this. I'm going to have to multiply both sides by y minus 2. That way they cancel on the left side. So I have xy minus 2x on the left equal to just 1. Let's see, I want to get the y by itself, okay? And so in this case, I need to factor out the x. And so if I factor out the x, then I get y minus 2 equal to 1. Now I can divide both sides by x. So those cancel. So y minus 2 over 1 over x. And then if I add 2 to both sides, although this is correct, I'm going to end up with a slightly different form than what our textbook, well, I'll go ahead and finish this. So let me go ahead and add 2 to both sides. This is going to be 1 over x plus 2, and then our inverse function is of x, inverse of x is going to be 1 over x plus 2. Now our function up here says 1 plus 2x over x. So how do we get that from what I have? If we go ahead and combine this with, or write this rather as a single fraction. Now, what should happen in our homework is the homework should take 1 over x plus 2 because those are equivalent expressions. If I'm trying to get those to match, then I need to go ahead and get common denominators. Common denominator is going to be x, so that would be 1 plus 2x over x, which is what the publisher says our answer would be. So same answer overall. So if you get one item and you take a look at somebody else, you're working with them, they say, oh, I ended up with something a little bit different, that might explain the reasoning. Okay, so we've got that. Okay. And this says check the answer. We're going to go ahead and skip that check for right now, because we've done several of those, and for our homework, there's really no good way to check that as well. So letter B, find the domain and range of f and of f inverse. Okay, so let's go ahead. Let's find the domain of f. So let's see. F of x over here was 1 over x minus 2. That was our original function. When we take a look at that, we say, well, our denominator then is not allowed to be 0, so x is not allowed to be 2, which is how we end up with that particular answer there. Now we want to find the range of f. Okay, so this is a composite, or not a composite function, this is a rational function. And one of the things we looked at in previous video is our end behavior. So as x approaches positive or negative infinity, f of x over here will act like, okay, whatever our leading or highest degree terms are, both numerator and denominator. So it's going to act like 1 over x. And 1 over x, x gets really, really, really big, is going to end up approaching 0. Okay, so it's not going to be 0, it's going to approach 0. So that's going to end up being then a horizontal asymptote. So you can reference one of our previous videos on the horizontal asymptotes and the rational functions. That's what we're working on here, is rational functions. So if you've forgotten about that, need a bit of a refresher, go back and take a look at the video on rational functions. Okay. And so on that one, if we have a horizontal asymptote, that means y is never going to end up being 0. Now, so we're going to approach 0. On the left side of 0, if x is negative, then I got, say, negative 2 minus 2, so that's going to be negative. Let's see if I got negative 2, that's negative 2 minus 2 is going to be negative 4, so that's going to be negative. So it looks like on the left side, I'm going to end up being negative very consistently. And on the right side, we're going to end up being positive. So we're going to end up with a graph that looks something like this. Just very, very, very rough sketch as far as our end behaviors. Now, we do have that minus 2 in there, so that's really going to shift it over 2 spots. So we should have a vertical asymptote over here at 2. Okay. So that would be a little better description of our graph. Okay. One of the things we can do is let's just go back and plug that into Desmos real quick. So let's see what we have. So we have 1 over x minus 2. And so we do see that we have this vertical asymptote at x equals 2, and we have the horizontal asymptote at 0. Okay, so just a double check there. And then our inverse function, we're going to say is 1 plus 2x over x. So that's our reciprocal function. So that's the thing that we're going to end up with eventually. So that's where we're heading. Okay, but as we take a look at this, okay, if 0 is our horizontal asymptote and this is our basic graph, we hit every value except 0. Okay, so that's how we end up with this piece. Now let's talk about the domain of f inverse. So one of the ideas that we end up with in inverse functions, if AB is on the graph, or so if AB is on the function, then BA is on the inverse function. So I have my domain of f and my range of f. Okay, that'd be my A and my B. What that does then for, notice the B was the second piece in this group, which was the range. Now it becomes over here. So the range of f is now in the domain's position of f inverse. Okay, and the domain of f is in the range position of f inverse. Okay, so this was the f function, this is the inverse function, so the domain and range flip-flop each other, where we see that if I'm trying to find the domain, okay, so this would be the domain of f inverse. The domain of f inverse is really the range of f. So previously, let's see, if we take a look up here, we want to find the domain of f inverse. So that's going to end up being the range of the f function. So if in my f function, my domain was everything except 0, now notice these were y's, then over here, my domain is going to be everything but 0, but I switch it to x's. Okay? Because these are the x, y pairs, x, y pairs. Same thing with the range of f inverse. The range of f inverse corresponding to the domain of f. So the domain of f, I was not allowed to use 2. That means in my range of f inverse, I'm also not allowed to use 2. What we do, though, is we just flip-flop the x and the y's. And then the last thing, we go ahead and graph both of those. We already did that on Desmos, and we can see where they match up, and that would be letter D. Okay, so we have finished up all of Chapter 6, Section 2 on one-to-one functions and inverse functions. Fascinating as far as how the basic notion is that they undo each other. Okay, so if I have f of f inverse of x, that's got to be the same as f inverse of f of x, which has to be the same as x. So if I take the function and I apply another function to it and I get back the same thing I put in, then I have what are called inverses of functions. And if AB is on one function, then BA must be on the other function. Okay. All right. So hope this video made a lot of sense. If you notice any mistakes, please go ahead and let me know. Otherwise, college algebra students, I will see you in another video, probably Chapter 6, Section 3.